Density is a great way to relate the mass of a substance to the volume of a substance. Now, mass is how much it kind of like weighs, if you will. Volume is three-dimensional space. Volume is usually listed in milliliters, or what's called a centimeter cubed. That's cm with the 3 in the upper right-hand corner. Mass in chemistry is usually done in grams. And substances will layer themselves according to their density. So, for example, if you throw a rock in the water, the rock will almost always sink to the bottom. That's because most rocks are more dense than water. The more dense thing goes to the bottom. On the other hand, if you spill some oil in water, and please don't do that, it's an environmental mess, the oil will float. Oil is less dense than the water, so it's on top. So this superposition is something that's really important, not just in chemistry, but all kinds of fields, to figure out what it is. Going back to the gold and the mercury examples from earlier, gold is more dense than liquid. So you can see that 19.3 is a bigger number than 13.6. The gold would go to the bottom. And the units of density there, grams per centimeter cubed. Grams is mass, centimeters cubed is volume, so it's like mass per volume. Here's a problem you might see when it comes to density. This is, say we have a piece of copper, it's a rectangular piece of copper, and the mass is 57.54 grams, and the piece of copper has a length of 9.36 centimeters, a width of 7.23 centimeters, and it's 0.95 millimeters thick, so not very thick, all right? We can actually use this information to calculate the density of copper. And again, density is mass over volume, grams over centimeters cubed. If we're going to do this, all right, the mass part, we've already got the grams, but we're going to need a volume, and a volume in centimeters cubed. And what that means is we've got to get everything in centimeters before we can do any calculations. So let's turn 0.95 millimeters into centimeters. And if you look this up online, or you happen to know, there are 10 millimeters per 1 centimeter. And if you have a millimeter on the top and a millimeter on the bottom, they cancel. So 0.95 divided by 10, 0.095 centimeters. And now that we have the thickness in centimeters, the volume will be length times width times height. And notice here how it's centimeters times centimeters times centimeters. And if you throw this in your calculator, it comes out to be 6.4, and that's 6.4 cubed centimeters, or centimeters cubed. That's the volume of the copper. We can use this then to calculate the density of the copper. Density is mass over volume. So 57.54 grams divided by the volume there, 6.4 centimeters cubed, 9.0 grams per centimeter cubed is the answer and stuff for the density in this problem. Now, if you actually do this in your calculator, you're going to get a different number than 6.4. The calculator will kind of go on and on and on. And I have applied here some significant figures, which is something we'll talk about later, to this problem. So for right now, just take it as a leap of faith that there's a method to the madness and that the density comes out to be 9.0. And later on, I'll talk about how we got those numbers and why I cut them back so much, like in this problem. So here's a question. It says we have a piece of metal. The mass is 33.2 grams, and it's basically placed in 10 milliliters of water. And the question is, what's the identity of the metal? Now, if you look at the little picture on the right-hand side, it starts off at 10 centimeters cubed. And by the way, a milliliter and a centimeter cubed are the same thing. It then goes up to 22.3 centimeters cubed. And the question is, what's the density of the metal? Notice I said density there. If we know the density, we can use the list of possible choices to find the identity of it. So on this problem, this makes sense to first find the density and then find the identity. And this problem uses what's called the Archimedes Principle to figure it out. And what Archimedes' principle is all about is basically if you add a rock to water, the displacement of the water is equal to the displacement of the solid, i.e. the volume. So we're going to use the difference in volumes there to figure out what the volume of the metal is. So mathematically, this is not really a hard problem. Mass of the metal, 33.2. Volume of the metal would be 22.3 minus 10, or 12.3. So in this problem, the density comes out to be 2.70 grams per centimeter cubed. And again, you get that by mass divided by volume. And you want to use the displacement system. And Archimedes is this person that supposedly was in the bathtub, and he sat in it, and he realized the water went up as he sat down. And he's like, oh yeah, okay, the volume displaced is equal to my volume. And he used it for metal. And supposedly it helped them to solve this problem they were having with fake gold versus real gold, which is kind of cool. So the number that you calculate, 2.7, is certainly closest up here to AL, answer E, so that's where this one comes from. The densities of the elements are all over the place. They generally on the periodic table tend to bulge around the middle part. The osmium and iridium, you can see, are bigger than all the other ones. There are some distinctions. We'll talk more about them and stuff, but all substances arguably have a density. Some of them are very similar to each other, but some of them are quite different. So a lot of times identifying an unknown is as simple as just finding the density of the item. Density is an intensive property, which means it doesn't mean how much of it you have. So you can have a little bit of brick or a lot of brick. The density should be the same. The relationship between the mass and the volume will not change depending on the quantity. And this is a cool distinction. Things like boiling points and melting points also don't matter as to the quantity. You can have a little bit or a lot, should be the same boiling point. Now that's quite different from extensive. Extensive means that you do need to know how much you have. So mass, for example, is extensive. 5 grams is a lot different than 500 grams. So you'd have to know like how much mass you have. But density, as long as you have just a little bit of it, you're good to go. It'll work for the bulk, which is kind of cool. Here's a problem. Mercury, quicksilver, has a density of 13.6 grams per centimeter cubed. And it says, what's the mass of 95 milliliters of mercury? What's the mass in grams and in pounds? And this is a typical kind of problem that involves density. And if you're going to do problems like this, and like most problems in chemistry, you're going to use this process called dimensional analysis. And dimensional analysis, which is sometimes called factor label, just means that you're starting with some kind of unit and you're converting it to a new kind of unit. And along the way, you need a conversion factor. You need to know what you're starting with, and you need to know what you're ending with. So on this problem, you are starting with 95 milliliters of volume, and you have certain types of units here. You have a density, all right, and you want a unit in grams, and you also want a unit in pounds. So notice here what I'm doing. I'm figuring out what my starting unit is, and I'm also figuring out some conversion factors to get to the units we want. We want grams and we want pounds. 1 centimeter cubed is the same as 1 milliliter. And I kind of babbled about this earlier with the problem on the other thing, but a centimeter cube is length, width, and height all equal to a centimeter. And that literally is what a milliliter is. It's a milliliter of volume. So you can interchange milliliters and centimeters cubed all the time. So up there it says 95 milliliters. You could call that 95 centimeters cubed, and that's totally cool. Centimeters cubed are usually used for solids, while milliliters are usually used for liquids, but again, you can interchange them if you want to. It's not a problem. So in this problem, let's call it 95 centimeters cubed. Let's skip right to it, because a milliliter and centimeter cubed do the same thing. And then if you multiply it by the density, notice that your starting unit, 95 centimeters cubed, the centimeters cubed, they cancel out. Centimeters cubed over centimeters cubed would be like x over x in math. It's just equal to 1. So those units cancel out. And grams is the only unit left forward. So 95 times 13.6 is 1.3 times 10 to the 3, or 1,300 grams. And that's the answer for mass in grams. Before we do the pounds, notice we started with 95 centimeters cubed, 95 milliliters. We used a conversion factor, and we canceled out the starting unit, and we ended up with the desired unit. And that's really what dimensional analysis or factor label is. You're starting with something, you're using a conversion factor to cancel it and get to your desired unit, and you're good to go. Sometimes there might be more than one conversion factor, but that's really all this comes down to. Now, the second part, we need to try to figure out the mass in pounds, and you're going to need a conversion factor for that. Now, if you happen to know the conversion factor, cool. If you don't, it's about 454 grams per 1 pound. So now what I would do is you're starting with grams, you want to cancel the grams, and you want to have pounds. So in this next part here, then, you'll put the grams on the bottom and pounds on the top. The 454 goes with the grams, so that goes on the bottom. Grams divided by grams cancels out. You've got just pounds. The abbreviation for pound is LB. In your calculator, you'd go 1.3 times 10 to the third divided by 454. No reason to multiply by 1 and then divide by 454. That's too much work. So 1.3 times 10 to the third divided by 454, 2.9 pounds. Again, I'm cutting some of the numbers off from what you're getting in the calculator because of significant figures, and we'll talk about that here in a little bit. Volume is really interesting, and again, there's a couple different ways to do it. If you've purchased soft drinks in the store or something like that, a lot of times it's in liters or milliliters, all right, which is totally fine. But solids, a lot of times, will use length times width times height units. So, for example, a centimeter cubed, we've seen a lot already. And the important part, more important than anything, I would argue, is that a centimeter cubed and a milliliter are equal to each other. Now, there are 1,000 milliliters per liter, so that would mean 1,000 centimeters cubed in a liter as well. Sometimes, especially in science and physics, they'll use meters cubed, no problem. You can convert meters cubed into centimeters cubed and stuff like that. And we'll talk about those in a little bit. But just realize that's what it is. It's literally three-dimensional space, all right? But the important part for us in chemistry is that a milliliter and a centimeter cubed, same thing.